Hello GTS 300 and welcome back to the 9th lecture, and this week we're going to be focusing on two sample difference of means tests. So well done for submitting assignment 6. I think pretty much all of you now have actually submitted that assignment. Today I'm going to be setting assignment 7, which basically will set you up for submission in 7 days time on October the 28th. I've heard from some of you, and some of you have definitely been working towards getting those answers right, so I think that's really good. Don't hesitate to reach out to me if you're stuck on anything for this next week, week's worth of assignment coursework, essentially, okay? So let's get stuck into the content today. You'll notice that as we start to get into these more sophisticated statistical tests, there's basically less qualitative information in these lectures, but you have kind of more complicated equations that you need to kind of get your head around. So basically, this will probably be a shorter video than the others. They will be for the next few weeks, but then you'll have maybe more time to go over that work within R in order to kind of understand exactly how these tests are carried out in practice. And obviously, we've covered now the descriptive part of the course, and we're focusing very much on the inferential statistics component over here. And I just wanted to introduce this flowchart of commonly used tests within statistics, because I think it provides you with a really kind of useful way to understand which data analysis technique you might need to use given your particular research question, your data types, things like this. Okay, so if you have continuous data, as we have today, we're focusing on the differences, for example, between two means or maybe also two proportions. And then we're focusing explicitly here just on the means. And then we've got two treatment groups. Basically, if we've got normally distributed data, we'll be focusing on the students' unpaired t-test and the paired t-test, which is what we'll be going over today. And then also if we've got non-parametric data, okay, so data where we haven't transformed it into a parametric distribution, so we're having to work on it as non-parametric data, then we'll be focusing on the Mann-Whitney U or the Wilcoxon-Rank sums test, okay? So that's basically how we get down into what we're going to be covering today. Next week, I'm pretty sure we'll be going on to analysis of variance tests over here. And then I think also within the rest of the course, we'll also be covering correlation, regression, and also analysis of discrete categorical variables. Okay, so what are we going to be covering today? Well, firstly, we're going to focus on independent samples. So what does that mean? Well, that means samples that you've collected maybe for two different places. Maybe you capture house prices within Fairfax, and you capture house prices within Richmond, and then maybe you want to compare those two different places to see if they're significantly different from each other. They would be independent because they're from two separate places. And then this kind of contrasts with dependent samples, which maybe what you do is you evaluate the house prices just for Fairfax City, and you do it in 2019 at the start of the year before the coronavirus pandemic, and then you evaluate it this year, so it's at least 12 months after, maybe 2 years after then, okay, the kind of the start of the coronavirus pandemic, and you evaluate those house prices, and you're basically picking the same individuals, but just at a different period in time. That would be the same sample essentially, and therefore the results are dependent on each other. So this is why you have these two different approaches, because they measure different things, and there would be different errors basically. And then within that, we've got the kind of the tests which focus on the normally distributed data, and the tests which focus on the non-parametric, non-normally distributed data types, okay? And we'll cover these today. So the two sample difference of means, the two sample difference of proportions test, the Wilcoxon rank sum test, and then matched pairs t-test, and then the Wilcoxon matched pairs signed ranks test, okay? So let's get into these two sample tests, and we're going to cover a few of the concepts around these statistical techniques first. So last lecture we focused on one sample, so we would just collect a data sample and we would just see basically where it sat within the distribution relative to what we would expect to occur randomly if we just randomly went out and selected a bunch of individuals within our sample, and then we use a certain confidence level in order to estimate how those one sample tests were carried out, okay, whether we thought they were significantly different from normal or not. This week we'll be focusing on 2 samples. So again, as I kind of mentioned before, this will be focusing on maybe 2 different cities and looking at something like crime rates or house prices, maybe testing if 2 different forests have different mean tree heights. You could do an infinite number of different tests like this using 2 different samples, okay, depending on whether they're independent, they're from separate places, separate people, or whether they're dependent, so where you use the same sample subjects, but maybe you sample at different points in time. And as I mentioned before, here we're interested in whether the samples are actually significantly different for each other. And if they are, then we can conclude that the samples were drawn from different populations, okay? If the samples are not significantly different, then basically we can conclude that the samples were drawn from the same population, okay? So this is the kind of key significant difference with regards to how we interpret this set of tests. So for data types, for one sample tests, we had different tests for different types of statistics, and we'll be kind of reflecting those again within this week. And I've already kind of mentioned that I'll be focusing on the mean in some examples and focusing on different proportions in another type of test. The data type will obviously have an impact. So I've kind of mentioned this before, which is that if we're focusing on parametric data, we're going to be focusing on continuous interval ratio data, okay? And then it basically, if that distribution of that data does not conform to the Gaussian, so the bell-shaped curve, the normal distributed shape that we would expect, then basically that will mean that we have to use a non-parametric test in this case. And that will mean that we might have to downgrade our data from continuous data into nominal or ordinal groups, okay? So we might have to do that within the practical session. So hopefully I'll be able to kind of show you how you do that. Basically, you're taking continuous data and you might then use ranges and you basically put it into ordinal data. So you convert your continuous metric into a set of categories which have some sort of underlying order, okay, to represent the data points. Independence. So I've mentioned this many times before because I've spoken about as randomly sampling and making sure that our data techniques conform to that requirement that our samples and the data that we collect are independently produced. So for independent samples, if we have a 2-sample version, then this is basically when the sample is unrelated. So I mentioned already we could sample 2 different places, whereas the matched pair version is where we basically use the same people or the same properties again before or after an event. Okay, so this is more commonly used, this matched pairs version, if we maybe got time series data, so there's some sort of temporal dimension to it. Whereas this 2-sample independent version could be time, it could be related to space, so it could be different phenomenon altogether. So independence of data is an issue which we persistently come across within statistics, okay? And I will continue to raise that as we move towards the end of term and start to get into things like regression modeling, okay? So a few more points. There's only one 2-sample test of proportions that we're going to cover, and independence doesn't really matter so much for proportions, but it's really important when we get to means. The same hypothesis testing procedure will be carried out. The hypothesis testing procedure is central to the way that we carry out the 2-sample tests, but we're not going to go through those 6 steps that we went through in the previous lecture. Basically, we're going to be using p-values. So basically that means that this will be indicative of whether there's some sort of significant finding that we're finding with the test statistic that we've just produced from the data sets. Okay, so if the p-value, if we want to be 95% certain that the results haven't just occurred randomly by chance, then basically the p-value will need to be lower than 0.05, okay? And if it's lower than 0.05, then we're able to say at the 95% confidence level that the results haven't just occurred at random, and that these results that we have obtained are significantly different, okay? In this case, for 2-sample tests, it would be that those samples have been taken from significantly different populations, okay? So they're not part of the same population. Okay, 2-sample tests. Let's get into some of the meat now. So think I've covered most of this already, independent geographic samples. And so this is where we may compare two different cities based on their average house price. And obviously we have these different tests, which I've already covered, so I don't need to go into much more detail here. I think it's fairly straightforward for the parametric types, but for non-parametric, we're going to be focusing on this Wilcoxon rank sum W test, which is essentially the same as the Mann-Whitney U test, but it's easier for us to calculate, okay? And we like things that are easy for us to calculate. So getting into the two sample difference of means test, the objective here would be to compare the means of those two independent samples for difference to see whether they've been taken from two different populations. So the requirements are that we have two independent samples which have been randomly obtained, and that the data in one of the samples are not related to the data from the other sample, okay? We assume that the populations are both normally distributed and that we've got continuous interval ratio data. For the hypothesis, here this is the null hypothesis, this H0, and that's basically where we would expect that the mean for sample 1 and the mean for sample 2 are essentially the same. Or here it would be if we subtracted the mean for sample 2 from sample 1, we would get 0, okay, because they would be the same. For the alternative hypothesis, this is where we say that we don't know whether the mean for sample 1 is larger or smaller, we just think that it's different, okay? So it's a two-tailed test, and that contrasts with the alternative hypothesis here, where we maybe have some sort of directional understanding. So where my mouse is here, this would be saying that the sample mean for the first sample would be smaller than the sample mean for the second, or over here it would be vice versa, so it would be the sample mean for the first would be larger than the second, okay? If we've got more than, 30 samples in each of the samples, 30 individual data points in each of the samples would be safe using the Z distribution. If we've got less than that, then we probably need to use the T distribution. And for this particular class, we're only going to use the separate variance estimate, not the pooled variance estimate for standard error. And we will just use the t-test approach. Okay, so what I'm doing is just basically saying that we're using a simplified way to make these calculations. Okay, I'm not going to get into how we carry this out and all of these different types of ways of making this estimate. We're just going to use this relatively simple form over here. Okay, so we're going to calculate either the Z or the T statistic depending on the number of samples that we've got. And actually this test is dead easy because all we're doing is we're subtracting the mean of the second test. You see here it's X bar, and this refers to the second sample. And we're subtracting it from the mean of the first sample, okay, to get the numerator there. So this is the difference between the samples. And then for the denominator, we're taking the standard error of the difference between the means, which is this sigma value here. And to get that, we take the square root of, and basically we have the squared standard deviation for the first sample divided by the number of samples in the first sample and added together with the squared standard deviation for the second sample divided by the number of samples in the second sample, okay? So this standard error of the mean is just accounting for the level of difference that we would expect to happen when randomly collecting samples, okay? So I think that this is relatively straightforward. It's not too complicated, and you just need to remember that basically the size of the test statistic is the key thing here. So if the test statistic is very large, it's saying that there's lots of difference between the two samples and they're not very similar. If the test statistic is very small, it's saying that they're kind of the same. So in summary, we're dividing the magnitude of the actual or observed difference in the sampling means, so this numerator up here, by the magnitude of the expected difference for the sampling means down here, so the denominator. So if the difference between the samples is larger, the test statistic will be larger. Okay, so that's just literally repeating what I said before, and hopefully that's kind of fairly clear to you now. That's kind of getting drilled into your brain that that's the way to interpret this particular test. Here's an example, and this example is taken from the book. It's the McGrew et al. Book, page 161, and basically the question is, well, does the involvement of women in the labour force actually vary depending on the level of economic development of the country? Okay, so economic development is widely measured by income groups. So you could look at the World Bank income group, and there will be low income countries, lower middle income countries, upper middle income countries, and then high income countries, okay, and that's generally how these sort of countries are grouped in different ways. We could then take maybe a sample of more developed countries, maybe there's 15 of those countries. We have a mean of participation in the workforce. I think this is 52.6%. The standard deviation is 7.82, and a variance of 61.1, and we could get the same for a sample of 45 maybe lower middle income countries which are less developed, and they would have some sort of mean of 51.2. I think that's percentage of participation of females in the workforce. I'll need to check that. And then basically 16.5, which is the standard deviation, and 272.5 as the variance. Okay, so now we're able to compare these different samples that we've got because we've got all the key ingredients in order to carry out our test statistic. So we're going to define a hypothesis. We're going to say the null hypothesis is that labour force participation in these two sets of countries is the same. Okay, there's no difference here. Whereas the alternative hypothesis would be that that labour force participation from each of these sets of countries is different. Okay, and we're not saying whether it's larger in one type or smaller in another. So there's no direction to it. We're not saying this is a one-tailed hypothesis. This is a two-tailed hypothesis, and we're saying there's some sort of difference, but we don't know whether it's in the lower part or the upper part of the distribution. So for the statistical test, you know we're going to be looking at this two-sample difference of means, and ultimately we will calculate this test statistic. Okay, so we only have 15 samples in one of the samples, and therefore, so 15 individual countries in one of the samples, and that means it's not large enough for Z. So we're going to use the t-test statistic and the t-distribution. Okay, so we need to calculate, before we get this t down here, which is in the middle, so this is the overall formula, we need to get the denominator here. So we're going to do that by basically inputting the values into this equation here. So so the standard deviation for the first sample is 7.82, the standard deviation for the second sample is 16.5, and we're going to square them, and then we're going to divide by the denominator, which is the number of samples. So it's 15 here and 45 samples here. And basically when we then we work through that equation, we add these together and we take the square root, we get 3.18, which forms the denominator in this main equation here. And then basically we need to take the mean for the first sample and the mean for the second sample and subtract them. Okay, so we're going to have this 51.2 value here for the second sample of developed countries and subtract it from the first sample, which is 52.6. So sorry, that's the mean sample for the less developed countries, 51.2. We're going to subtract it from 52.6, which is the more developed countries. And basically when we then carry out that equation, we get 0.44. Okay, so that's the t-statistic. So then we have to go and we have to see that t-test statistic is it's saying it's 0.44 standard deviations above the mean. We can then get a p-value for that in R, as we'll do later within the lab. And basically because that p-value of 0.65 is well above that 0.05 significance level that we're looking at in order to be 95% confident that our results haven't just occurred by chance, then essentially we would say that there's not enough evidence to reject the null hypothesis. Okay. So, and I also carried out this little calculation down here in Excel, so you can calculate it in R later in the lab session, or you can even recreate this data here in order to produce those numbers just using a simple spreadsheet. So what if the data don't actually conform to the assumptions that we have? Well, well done for even thinking about the statistical assumptions. That's a really good thing to think about. But I think the important thing is that we could be dealing with non-normally distributed data. Okay, so the data aren't normally distributed, therefore the results could be invalid if we're using a parametric test because we're not conforming to that Gaussian shaped curve. And then secondly, the data may only be available in ordinal or ranked form, okay? And if that's the case, then we're going to have to work with a different type of statistical test. So for the two sample difference of mean tests, we're conducting the Wilcoxon rank sum test is the most widely used. So you'll encounter the Mann-Whitney U-test too, but we're going to focus on the former. So here we are, here's the actual test. What are we trying to do with it? Well, we're trying to compare the rank sums of two independent samples for difference. So what does it mean when I say rank? Well, just remember that in some of the other classes we've ranked the data, so from low to high or high to low, and then basically we've put a number in each row and said, you know, once we've ranked them, we said this is row 1, row 2, row 3, rank 1, rank 2, rank 3, for example. And then basically we can then use that ranking that we obtain to identify if there are significant differences between the sample. So don't worry if this isn't clear, because I'll give you a real worked out example in the next part of the actual lecture. So here we assume that we've got two independent random samples. The population have the same shape as the normal, as the non-parametric distribution. We've got ordinal data here, okay, so we can actually rank them. If we've got ratio interval data, then we need to downgrade it into ordinal form. For the hypothesis, this is the null hypothesis, so we're basically saying there's no difference in the rank sums between the populations. The alternative is that there is a significant difference, so this is two-tailed here, or we could have a directed alternative hypothesis where basically we think that the rank sums for one group will either be smaller or larger than the second population, okay? And for the test statistic here, we're going to use this ZW. So how do we get that ZW? Well, basically we need to take the mean ranks of the W that we're going to produce and subtract it from the sum of the ranks for the sample I, and then divide it by the standard deviation of the W value that we'll obtain. So basically we get that W bar, that mean ranks value here by basically multiplying this Ni, so this is, I believe that's the sample size, multiplied by the sample size for the first sample, the second sample, and 1 added together divided by 2. Okay, this is how we get this Wi, and we'll calculate this later. We then basically do the same to get this SW, but we're taking the square root of this equation here. So it's fairly standardized around the actual sample sizes that you actually obtain, okay? So the steps, well, combine the samples into a single data set, which you can do in an Excel spreadsheet. If you don't want to do it in R, it's dead simple. We order and rank all of the sample data from smallest down to largest, okay? When we have tied values, then we basically allocate the average rank to those rows that are tied. And then basically we sum all of those ranks up for sample 1 and for sample 2. And basically we get the sums which form the W1 and W2 values. We then need to get this ZW. You can do the W1 or the W2. You have to just pick one. The only difference is the sign, whether you're getting a positive or a negative Z value. And then we can get the P value for that ZW value that we produce from either a Z table, or we can use, you know, P norm in R, whichever you prefer, and then we can use that to make a decision, okay, about the samples. So does the involvement of women in the labour force vary by economic development of different countries? So we have the same data set again, and we're just going to run it through this calculation for the ZW test statistic. So we have 30 samples for lower income, 30 countries, and we have a W1 ranking of 746.5, and that compares with this higher income group where we have only 14 countries, and then we only have a W2 of 243.5. Okay, so the second sample size here is smaller than the sample size for the first group. So this is the one that we're going to use, the Wilcoxon W. So here's this W2 value that we're producing for this group here. And essentially what we're doing is we need to run through this equation, okay? So this N2 value here is 14. We then have the N1 and the N2 sample size, so 30 plus 14 plus 1 divided by 2, and then we just multiply those together and get 315. And then we basically put those pieces of information into this other equation down here to get the SW value, which is 39.67. And then we get the ZW statistic by subtracting that 315 for the mean of that second sample from this 243.5, which is the W value which we got for this sample. And then we divide it by 39.69, which is the value which we got here for this SW. And basically we get minus 1.805, which if we then use the p-norm for a function, for example, in R, we'll get a p-value of 0.071, which again is not significant. Okay, so what this is saying is those samples, both when we did the parametric test and the non-parametric test, are basically taken from the same population. They're not from different populations, and they could have just occurred by chance at the 95% level. Okay. And I think, when you think through this logically, that makes sense, because in some very low-income countries, you can have very high female participation in the workforce, which, is fundamentally a good thing, in my opinion. And then in other countries, you might have very high incomes. Okay, you might, if you look at Saudi Arabia, for example, you might have very high incomes, but you might have very low labour force participation in the workforce. Okay, which is basically suggesting that the level of female involvement in the labour force is probably highly dependent on kind of cultural factors, and maybe isn't directly dependent on the level of economic development as we measure it here by income group. Okay. Okay, so what do we do then if we have different samples and we want to measure the proportions of those samples and compare them together? So as long as we're taking independent sample proportions here, we can use this approach. As long as we've got independence between them and the variable that we're measuring is actually binary. So we need to identify our null hypothesis. So this row 1 for the first sample is equal to the row 2 of the second sample. And the alternative hypothesis would be that the row for the first sample and the row for the second sample are not equal to each other. Okay, so remember that this value here that looks like P is the Greek letter rho, and that's focusing just on a two-tailed hypothesis here, where we basically say that there's no difference. There is a difference between the samples we hypothesize, but we don't know whether it's larger or smaller depending on the sample. And that contrasts with our more directional hypotheses here, where we might say that the second sample is larger in its proportion than the first sample, or vice versa, where the first sample is larger than the proportion in the second sample. Okay, and then we get this t statistic, which is this CP value here, and that can be obtained basically by getting the difference of the proportions between the two samples. So you're subtracting the samples to get the numerator. And then essentially we can get the standard error of the difference of the proportions for the denominator here, and we do that by basically running through this math. So you need to get this this row hat here, so you can see the little hat that this character is wearing. That's just to indicate that there's something special about this, and that's that you need to calculate this statistic first down here by running through this particular equation. And then you can work through this part as well. Okay, so I think that this should be fairly straightforward. I'm not going to talk through it qualitatively, but basically if you know how to put these values into these equations, which I'm sure you do because we've gone over them all in very similar contexts in previous lectures, then you'll be able to calculate this test statistic. So let's move on to matched pairs now. So those previous examples, they were just maybe two different places and the entities in the samples were completely different. They weren't related in any way. Whereas what you might actually do very often is you might want to sample one place, and then over time you want to come back and you might want to sample it again, and that would mean that the samples are actually dependent on each other. Okay, so I think I'm just literally pointing here to what I've already discussed, so I don't think I have much more to say on that particular slide. We can just get into the objectives, the assumptions, the hypotheses, the test statistic for this particular approach. So we're going to focus first on the matched pairs t-test, and the idea here is for us to compare whether these two samples have come from the same population, given the fact that they're dependent on each other, or whether they're coming from different populations. So we need to have a random sample. The paired data then requires that we match the samples. So if I go to one property to get the house price in 2019, and I go back to that same property in 2021 to get the same house price, then basically that would form this XI and YI entry here. So we then need to have those paired together within our spreadsheet or R or whatever it is. The populations we assume come from normal distributions, and we use interval and ratio data. And we're using this delta value here to indicate the actual hypothesis that we're going to have for these samples. Okay, so for the null hypothesis here, we would expect this delta to be 0, no difference between the samples. Whereas if we have this alternative hypothesis here, which is two-tailed, so we're not saying whether we think it's smaller or larger, we're just saying that the samples are different, and therefore this delta value is significantly different from 0. We could also have our directional hypotheses here. And the test statistic we're going to try to obtain is this TMP value here, this test statistic. And basically we get that by basically taking the mean of the matched pairs difference here as the numerator. And the way that we do that, this d bar is basically to sum all of the di values, and the di's are just the difference for the matched pairs. Okay, so I'll show you how we calculate this later. It's just the yi value subtracted from the xi value. And then we divide it by the number of samples that we've got in this sample, and that gives us this mean of the matched pairs difference. For the denominator, then what we have is this standard error of the mean difference, which sounds really scary, but it's very similar to what you've calculated before. So this is basically just the standard deviation of those matched pair differences, okay? So you should know how to calculate this now. Let me give you an example, okay? So let's use the example from the book. And the question is, well, does the historical temperature data set show an increasing data trend? Okay, and we're focusing on this average annual temperature for weather stations in the American Corn Belt between 1974 and 75 versus 1994 and 95. Okay, so they're the season ranges, and we've got these two different time points for the 70s and the 90s. Okay, probably long before most of you were all born. Okay, and we have this data here. And basically we've got the 90s data on this column, we've got the 70s data in this column, and then we have the weather station name down here. Okay, so these are all places in the Corn Belt, so you'll probably recognize Kansas City, St. Louis, Omaha, Nebraska. Okay, and basically what we get for those D values is we need to subtract one from the other, okay, and we end up with these differences here. And then we can actually allocate ranks to them if that's what we want to do. So this time around we're not allocating ranks to them yet, and we're just focusing in this case just on the parametric version of the test. And basically we would be saying for the null hypothesis that our d value is equal to 0, and then our alternative hypothesis is actually going to be larger than 0. Okay, and the reason why we say larger is because we're asking if the historical temperature trend shows an increasing trend, okay, increasing trajectory. So we then have these key values that we've calculated up here. We need to basically do that d bar divided by this sigma d value here to get this TMP test statistic. So to get that d bar, what we need to do is we basically need to take the sum of all of the di values, which is 5.5, divided by the number of samples that we've got, which is 28. And that gives us 0.196. So we can put that in as the numerator for our equation here. Then we need to get the denominator, okay? So that denominator, this sigma d value here. The way that we do it is basically to get that standard deviation. So we need to basically get these two values that are going to go in here. Thankfully, we've calculated the sum of the d squared values, which is 7.87. So we put that in here and we subtract this 108 value, which is basically the squared sum of the di values divided by the number of samples. And then what we do is we take the number of degrees of freedom here. So you'll remember that we did this in the previous class. So it's the number of samples that we've got -1, and that indicates the number of degrees of freedom. So with 28 samples, we would end up with 27 as the denominator. And then we can take the square root of the product of this equation, which gives us 0.501. So essentially we can go 0.196 divided by 0.501 divided by the square root of 28. And that gives us this 2.07. And then when we actually find out the p-value for that 2.07, obviously that's large, and that's going to be indicative of the fact that So you can think of this as standard deviations. You can then basically get this p-value, and that p-value is very small. It's below that 0.05 level that we're looking for in order to get that indicator that these results may be significantly different from what would just randomly occur, okay? So it's 0.027 here at 27 degrees of freedom. And because this is significant, we therefore reject this null hypothesis that there's no difference between the before sample and the after sample. What we're saying is that we're accepting the actual hypothesis that we have, and it's directional. We're saying that there is an increasing temperature trend, okay, at the 95% confidence level. Then hopefully we've got the right answer for that particular example, okay. So you can read more about that in the book if you want. Obviously, we have that same old problem, which is, well, what do you do if your data don't conform to the test assumptions? And you know, this has happened a lot to me. Most of the time that I was doing statistical analysis in my undergraduate degree, I never really had normally distributed data. So I ended up having to use either transformations to make the data normally distributed, or to basically convert it into non-parametric data style in order for us to actually use those tests. So if the data are ordinal, it's not going to work for that matched t-test, matched pairs t-test approach. And basically, if the data are not coming from normally distributed population, then also it's not going to be appropriate. Also, the sample sizes might be too small for the parametric approach that we stated here. So the Wilcoxon signed rank test is another parametric equivalent that we can use for dependent samples, okay? So what are we doing here? Well, basically we need a sample that's randomly collected. We need paired data again for before and after those time periods. We assume the populations do not have a normal distribution. You can demonstrate that for yourself. Maybe you've tested for the normality of the data and it's not been normally distributed. And then we've also got ordinal data, okay? Either we've taken our continuous data and we've downgraded it into ordinal ranks. So the hypothesis here would be that there's no difference in the ranked matched pairs compared to the alternative hypothesis, where we would say that there's a significant difference between these two samples that we've obtained. Okay, and we want to get this CW statistic here, which is based on this larger equation than what we normally use. So if we just look at the denominator here first, most of it's straightforward, okay? So we're taking the square root of the number of samples multiplied by the number of samples plus 1 multiplied by 2 times the number of samples plus 1, and then divided by 24, and that gives us this bottom part of the equation. And then essentially in the numerator, and I left this till last, is because we need to calculate this t, which I'm going to show you how to do in the next slide, and subtract basically n multiplied by n plus 1 as the numerator divided by 4. So this test that we're talking about here, which we will cover within the laboratory session, uses matched pair differences ranked from lowest to highest. And the absolute difference is used between the two variables to determine the rank rather than the positive or negative values. When the difference is 0, we ignore the item within the ranking. When the differences are tied for a particular rank, we allocate the mean to that particular rank, okay? But the challenge, therefore, is, well, how do we decide this t value that needs to go up here? So what we do is we basically we have to get these matched pair differences which are ranked from lowest to highest in magnitude. And the sums of the ranks for the positive differences equate to this value here, Tp, and the sums of the ranks for the negative differences relate to this value here, Tn. And then basically, if we have a one-tailed hypothesis, then we use the t with the smallest number of differences. And if we've got an alternative hypothesis which is two-tailed, then we use the smaller of either Tp or Tn. But you might get a similar result, but there are these specific rules that we have to follow in order to use this equation and select the right t value. So in McGrew et al, there's this example on page 172, which basically covers the daily indoor water usage before and after a water reduction program. And we have all of these household IDs here. on the left-hand side for these 11 families, and we have the number of gallons of water that were used by the households before the water reduction program and the number after. And then we can calculate the change between these two values here. We can allocate the ranks, okay, so you can see that these ranks relate to the absolute values, okay. So what that means is that ignore the positive and the negative bits and then rank them from smallest to largest. And basically you're going to end up with 1.8 being the smallest, and at rank 11, 27.5 will end up being the largest, okay. And you can calculate the x bar, so the mean of the x sample and the mean of the y sample here, which gives you 152.8 and 146.5 respectively. And the Tn, okay, so it's this, the sum of the ranks for the positive differences is 47, and the sum of the, for the negative differences is 47, the sum of the ranks for the positive differences is 19. So we can then put all of that together. So we know that we're going to use this Wilcoxon matched pairs signed ranks test because that's what we're setting out to use here. It's non-parametric. It allows us to compare these different samples. And we've got the actual test statistics, which I mentioned before. So the number of samples is 11 households. The number of positive sum of rank values is 19. And the number of negative differences is 47. So the hypothesis would be that there's no difference between the periods, so before or after, it's the same, there's no difference. Whereas the alternative hypothesis would be that because this is a water reduction campaign, we actually get a reduction in the amount of water that's used, okay? And we need to select the T for use here, which corresponds to the smaller number of hypothesized changes, okay? And TP is the smallest. So basically what we do is we input all of those data variables, which I've put up here into this equation. We're using 19 as the T, and when we crunch through, we end up with minus 1.245. And we can put that into our p-norm function, and that tells us that we would get a probability of 0.1066. Okay, so that is, it's not a significant finding here. And therefore, as a consequence of that, we don't have enough evidence to actually reject the null hypothesis, okay? So basically what's happening is that there wasn't a significant reduction which happened after the water reduction campaign that couldn't have just occurred at random, okay? So there wasn't a strong enough of effect for us to significantly say that this water reduction campaign unfortunately actually had a significant impact on water reduction. Okay, so I appreciate that that was long, and we're talking about lots of statistical tests here which can be fairly dull for you, so just stick with this content. Make sure you tune in for the laboratory session now, where I'll go through basically how we calculate these different tests within R, and hopefully that will kind of put into your brain a little bit in a little bit of a clearer way how we actually carry out these tests in practice, because I appreciate this is quite abstract and high level, okay? Thanks very much for tuning in. It was really nice to see you all, and I'll look forward to seeing you in the next lecture. Thank you. Goodbye.